Welcome to this lecture on bugs as insect vectors. Today, we are going to explore how some of the smallest creatures on Earth can transmit significant diseases to humans. We will learn the biology behind their feeding habits and, more importantly, the mathematics behind controlling them. By the end of this video, you will understand exactly why public health interventions work. To start, think of a delivery driver whose job is to drop off packages at specific houses in a neighborhood. Now, imagine if that driver was a tiny insect. The package was a dangerous microscopic parasite, and your bloodstream was the delivery address. This is exactly how certain bugs operate in the natural world. They sneak up on us while we sleep, acting like tiny walking syringes. Unfortunately, while they take our blood for their own survival, they can accidentally leave behind diseases that cause lifelong health problems for the host. Now that we have an intuitive picture, let us define what a bug actually is in a scientific context. In everyday language, people use the word bug to describe almost any creepy, crawly insect. But in medical entomology, a true bug belongs to a very specific taxonomic group called the order Hemiptera. These insects are uniquely characterized by their piercing and sucking mouthparts. These specialized mouthparts are perfectly adapted for extracting fluids from their hosts, which is exactly why some of them have evolved to feed on human blood. Building on that definition, let us look at the most medically significant group of true bugs. These belong to the subfamily Triatomini, commonly known as kissing bugs. They are the biological vectors for a parasite called Trypanosoma cruzi. When this parasite enters the human body, it causes Chagas disease, a severe illness that can lead to fatal heart failure years after the initial bite. Understanding these specific bugs is absolutely critical for global public health, especially in the Americas, where this disease is endemic and affects millions. You might be wondering exactly how the kissing bug passes this dangerous parasite to us. Unlike mosquitoes, which inject parasites directly into your bloodstream through their saliva, kissing bugs have a much grubbier method. They transmit the parasite through their feces. While the bug is feeding on your blood, it simultaneously deposits feces on your skin. When the sleeping person scratches the itchy bite, they accidentally rub the infected feces into the open wound, allowing the parasite to enter the body and begin the infection cycle. Before we move on to the mathematics of disease spread, we must mention another famous true bug, the bedbug, from the family Simicidae. Unlike kissing bugs, bedbugs are primarily considered mechanical vectors or severe nuisance pests, rather than biological transmitters of disease. However, their global resurgence has caused massive economic losses, particularly in the hospitality industry, and they cause severe psychological distress for individuals. Studying their behavior and life cycle is just as important to protect our increasingly interconnected world from rapid infestations. To truly understand how dangerous a population of bugs is, scientists use a mathematical concept called vectorial capacity. This formula helps us predict how many new infections a single infected person will cause in a population. Let us break down the first few symbols. C is the vectorial capacity itself. The variable m stands for the ratio of bugs to humans, telling us how crowded the environment is. The symbol A represents the human blood index, or the number of bites a single bug takes per day. Notice that A is squared. This is because the bug must bite twice to transmit disease, once to acquire the parasite and once to pass it on. If the biting rate increases, the capacity shoots up dramatically.
Continuing with our formula, let us look at the remaining variables, which relate to the bug's lifespan. The variable p is the daily survival rate, meaning the probability the bug survives from one day to the next. The exponent n is the extrinsic incubation period, which is the number of days it takes for the parasite to actually become infectious inside the bug. Finally, the denominator, negative natural log of p, represents the daily mortality rate of the bug population. If the survival rate p decreases, perhaps because we use insecticides, the overall capacity, c, drops significantly. This math tells us exactly which part of the bug's life cycle to target. Now that we understand the formula, let us see it in action with a concrete example. Imagine a rural village where the ratio of kissing bugs to humans is 10. The bug bites once every 4 days, so A is 0.25. The daily survival rate is 90%, and the parasite takes 15 days to develop. First, we square the biting rate. Then we raise the survival rate to the power of 15, showing that only about 20% of bugs live long enough to become infectious. Multiplying these gives our numerator. We then find the mortality rate for the denominator. Dividing them gives a vectorial capacity of approximately 1.22. This means one infected person will generate about 1.22 new infectious bites per day, allowing the disease to spread. This formula we just used leads us to an important question. What happens if we intervene? Suppose public health workers spray the village with insecticide, lowering the daily survival rate of the bugs from 90% to 70%. All other variables remain exactly the same. We recalculate the survival probability and it plummets to less than 0.5%. The raw transmission potential in the numerator is almost entirely wiped out. The mortality rate in the denominator increases significantly. When we divide the new numerator by the new denominator, our updated vectorial capacity is 0.008. This is a massive reduction. Physically, this means disease transmission has been virtually halted because the bugs are dying before the parasite can develop. Having proven mathematically how sensitive this cycle is, let us visualize the physical transmission process we discussed earlier. On the screen, you see a diagram of the Chagas disease transmission cycle. Notice the sleeping human and the kissing bug feeding near the face. The critical part of this diagram is the small deposit labeled feces left on the skin. If you look at the magnified view on the right, you can see the microscopic Trypanosoma cruzi parasites moving from the feces directly into the bite wound. This visual reinforces why preventing the bug from living long enough to deposit infected feces is the ultimate goal of our insecticide interventions. We have covered a lot of ground today, so let us summarize the most important ideas. First, true bugs of the order Hemiptera are biologically adapted to feed on fluids, making them formidable vectors. Second, kissing bugs inadvertently transmit dangerous parasites like Trypanosoma cruzi through their feces, not their saliva. Third, we learned that vectorial capacity is a powerful mathematical tool that combines biting habits, lifespan, and parasite development to predict disease spread. Finally, our calculations proved exactly why targeting the survival rate of these bugs with insecticides is our best defense. You now have a solid understanding of both the biology and the mathematics of hemipteran disease transmission.